Hello, and thank you for joining our webcast today. We're going to be focused on high-speed serial link analysis. The presentation is going to be given by Ken Willis, a Sigrity Product Marketing Manager. He's been with the company for about a year. Before that, he had been with Cadence in engineering, marketing, and services positions. And before that, he had done a lot of work in the signal integrity area as a designer for computer companies like Compaq and telecom companies as well. Of necessity, this is a one-way audio broadcast, but we do want to hear your questions. So there's a chat window that you'll see at the bottom right. If you have questions throughout the webcast, please enter them in the window, and we'll catch up with them at the end. Now, some people did give us questions as they were registering. We got questions from San Jose, California, Longmont, Colorado, Portland, Maine, Austin, Texas, and Kerala, India. So we've woven those throughout Ken's presentation. Our focus today, as I said, is on high-speed serial link analysis and how to do this in a way that is accurate, fast, and doesn't require that you become a lifetime tool expert. So with that, take it away, Ken.
Okay, thanks. Hello, everybody. This is Ken Willis from Sigrity. I see a lot of familiar names on the registration, so hello to everybody and old friends and new ones as well. So today we're going to talk about multi-gigabit serial link analysis. As Leslie had mentioned, you can use your chat feature to post questions as we go throughout the presentation. We'll try to cover some of those at the end. Okay, so the agenda we have lined up for today. First, we're going to talk about some of the unique requirements for serial link SI analysis. Obviously, this has brought a lot of unique challenges to the SI engineer, and it's been a very dynamic space with lots of interesting work that's gone on and capabilities that we're going to share with you. We'll talk about how Sigrity has put together their serial link SI analysis flow so you can understand how the analysis is done. We'll see a little bit of correlation data. In the middle, we're going to take a break to do a brief demonstration and run the tool through its paces and show some of the capabilities there and some of the different trade-offs that you might make as an SI engineer working on these types of designs. We're going to talk about algorithmic SerDes modeling with IVIS AMI. We've had lots of questions on that. Power noise effects on serial link signal integrity, and then we'll go to questions. Okay? Okay, so starting off, unique requirements for serial link SI analysis. So, one of the questions is, we've done SI for a long time. Why do we need new tools? Why do we need new techniques just for serial links? What's so special about serial links? Well, one of the analogies that you can draw is to your experiences in the lab as you're looking at serial links and you're looking at eye diagrams, and you set the oscilloscope for infinite persistence. And initially, you might see an eye diagram that looks something like this. It's fairly open, and things are looking pretty good. As time goes on, though, after you initially trigger it, the eye diagram can start to close down a little bit. Hopefully, it doesn't go all the way to this point where it completely closes. That obviously would be a bad day at the office. But fundamentally, what's happening here is the sampling oscilloscope is taking a number of samples, looking at all different combinations of ones and zeros of traffic that comes in, and as it hits all these different unique combinations, it's closing down the eye diagram until eventually it stabilizes and stops. And when it stabilizes and stops, you can then take reliable measurements and look at the eye height and the jitter and so forth. Simulations are exactly the same way. You simply have to run enough traffic through these links, get enough samples in order to get a mature eye diagram. And if you don't simulate enough bits, you can get potentially a very optimistic result. So what we found, traditional circuit simulations just can't simulate enough bits to produce a stable eye for these types of multi-gigabit serial links. Okay, so this is one of the reasons, this is one of the unique requirements that you run up against when you're looking at serial link applications, is you simply need a way to simulate a lot more traffic than you're used to doing. So high capacity simulation is needed. It's very typical to need to run a couple of 100,000 bits to get good results that you can take judgment on, and maybe for final verification you may want to run in the millions or even a 10 million bit run to get your final margins. So and the more bit traffic you can run, the more stable you can get that eye diagram, the more accurate your bit error rate extrapolation can be, so you can predict what the BER performance of that link is going to be. Another unique requirement you'll see, besides the need to do high-capacity simulation in some manner, is the modeling of some of these modern SerDes devices. Many of them have now adaptive equalization, and what I mean by adaptive equalization is that instead of you going in and setting the equalization for specific settings, the SerDes transmitter or receiver will actually look at the channel, look at the characteristics of that channel it's trying to drive, and it will figure out its own tap coefficients and filter settings to what it thinks will optimally drive that channel. So that sort of adaptive equalization becomes very impractical to represent with traditional circuit models because there's really an algorithm in that SerDes that helps it figure out all of its optimum settings. And that unique algorithm really needs to be included as part of the modeling. Okay, so there's some unique modeling requirements today as well as unique simulation requirements. So taking a look at the serial link analysis flow that we've put together and how we address some of those challenges basically breaks into 3 steps. So the first step that we go through is to characterize the channel. And in characterizing the channel produces what we call the impulse response. I think the industry in the last several years, since the IBIS AMI standard came out, there's a lot more recognition of impulse response-based techniques. This has become a very familiar thing in the industry. The next is perform channel simulation, which in our case actually time domain channel simulation. We can do statistical analysis as well as another way to do that. But basically to generate the raw waveforms that you'll see at the receiver. Those raw waveforms are then post-processed to generate all the various outputs of the tool and ultimately let you look at your BER performance. So drilling down a little bit into those steps, the characterization of the analog circuit. So one of the fundamental things that happens is if you look at the overall serial link here for a through channel, we break out the output stage of the transmitter, typically with equalization turned off, whatever interconnect you have between, and the input stage of the receiver, and we break that off into what we call the analog channel. That's the analog circuit part of the channel. Okay. Then that analog channel is, in our case, simulated with good old-fashioned SPICE circuit simulation to produce the impulse response. Now, it's very important that this entire analog circuit is simulated together in its totality because these things interact real-time with each other. There's reflections between the transmitter and the channel and the input stage of the receiver and back and forth. So those things really need to be all characterized in one circuit to generate this impulse response. This impulse response is really the fingerprint of this channel and fully characterizes basically the transfer function of this whole system. And the impulse response is the input to the channel simulator, which is essentially a very high-performance advanced convolution engine, which will convolve this impulse response with whatever enormous bit stream you've asked the tool to synthesize for you. Okay. In that convolution process, what's produced is the output, the waveforms at the receiver. Okay. So this is sort of a snapshot of the overall process. So you've got circuit simulation to produce the impulse response. You've got convolution to produce the the receiver waveforms. And then you've got post-processing of those waveforms, statistical post-processing, to produce all the different outputs of the tool, eye diagrams and bathtub curves and so forth. Okay, so that's sort of a thumbnail sketch of the analysis flow that you can use to analyze these multi-gigabit serial links. Okay, so how well does it work? So we've had to do quite a bit of correlation on these techniques by virtue of the fact that we work with a large number of SerDes IP suppliers in the industry that are, many of them, producing their first IVUS AMI models. So we've had quite a few engagements like that. One key part of all those engagements is you need to correlate those models back to whatever golden source data they have, which is typically, in many cases, transistor level H-SPICE. So this is one example where we've got in the blue transistor level H-SPICE running at 10 gigabits with equalization from a telecom chip company that we've worked with. And in red, you'll see the channel designer results, which use, instead of transistor level, actually using behavioral SPICE for the I/O models and algorithmic models for the equalization in the transmitter. Okay, and you can see that the impulse response-based techniques with the channel simulator will faithfully reproduce the transistor level waveforms very closely. Again, assuming you've done a good job with your modeling. We also have some measurement correlation courtesy of John Montag at ECI Telecom. Shared with us some data that he had worked on, where you can see line card, backplane, paddle card, and the oscilloscope setup. This used some IVUS AMI models as well from a major FPGA supplier. And again, comparison of simulation results in Channel Designer and oscilloscope results. We're able to very closely reproduce what was seen in the lab. Okay. Okay, at this point, I'm going to take a break from the slides. We're going to do a quick demonstration, hopefully answer some more questions by showing you with the tool rather than talking through slides. So what I've got here is an example backplane topology. So you can build topologies to suit whatever application you have. We have a number of templates to start with. You can see some of the models that are available here used in this particular topology. You can see the transmitter model actually uses a behavioral SPICE subcircuit for the transmitter. The cards, I think we have W element files in here, and we have a circuit file in here, SPICE circuit file for the connector, and the backplane actually uses a touchstone file. So the fundamental approach here, from an ease of use standpoint, is to support basically whatever kind of models you have that are available. We want to be able to use in the topology to build out that die-to-die path. So if you have, encrypted transistor level H-SPICE models, or you have behavioral SPICE models, or you want to point directly to an IVUS file, W elements and H-SPICE syntax, subcircuits, touchstone, BNP format, any of those formats, you can plop right into one of these topologies and use them. And it's not relegated to just, so certainly Sigrity has very strong extraction capabilities with PowerSI, but if you use other solvers, you use HFSS or other full wave 3D solvers, and you have libraries of models from there in touchstone format, any of those are also certainly able to be put into these topologies. Okay, so what we're going to do initially is we'll just run a quick simulation, and you'll see that based on the process that we talked about, right now is running the a circuit simulation, which is doing the characterization step and generating the impulse response. And this is with initially with no equalization, just to give us a baseline. And again, characterization can be used either with Sigridy's circuit simulator SpeedSim or with HSpice. Okay, so the simulation complete. So that was 200,000 bits. So you can see that runs in a couple of seconds. Runs pretty quickly. If we look at some of the output, you can see that the eye diagram shows actually quite a bit of jitter. And we're going to need to make some improvements to this link in order to make it robust. One of the things we can do is turn on the transmitter equalization. There's actually a pre-emphasis model available here, which we can rerun. And we'll see what the improvement is on this particular link. Okay, so we can see there was maybe some slight improvement, but not really a lot of improvement there. There's obviously some more things we're still going to have to do. If we take a closer look at the AMI model associated with this, you can see there's actually two files associated with this particular element. There's the DLL, which is where the compiled code is. It contains the algorithm for this particular pre-emphasis equalizer, and an AMI model, which is really just a text file that allows you to set some parameters and configure that DLL model. The parameters from the AMI file show up here, and they're editable by the user. So one thing that we can do is, as an experiment, we can go and change this from a 2-tap driver to a 3-tap driver. And we can go and rerun and see what the effects are. Okay, so again, the fast simulation performance enables very rapid trade-offs. It allows you to do a lot of trial and error and what-if scenarios quickly. So this obviously made a big difference. So again, we start with no equalization. This was the 2-tap result. This was the 3-tap result. So you can see that opened up the eye quite a bit. Okay, and to get some insight as to what actually happened, let's look at some of the other inputs here. So these are the eye contours. Eye contours are just a lightweight way of looking at the eye diagrams. Makes it convenient when you're overlaying multiple results on top of each other, obviously. And of course, you can look at the bathtub curves. You can see in the blue, you can see how the bathtub curve opened up quite a bit with the 3-tap equalization. The noise bathtub also improved. You can see the impulse response, which was generated by the initial SPICE circuit simulation. They characterized the analog channel. But the interesting one really for this one is if we go take a look at the modified impulse response, which is the impulse response after the equalization had taken place. So you can see, if we look at the green result here, this was the impulse response, the modified impulse response with the 2-tap driver in place. And if you can contrast that with the result with the 3-tap driver in place, you can see down in this area, this is really the area where the major difference had taken effect. You can see with the 3-tap driver and the blue response, the modified impulse response is much sharper than this sort of lazy falling edge that you see here with the 2-tap driver. And the difference in that impulse response, the difference in that equalization is what really cleaned up the waveform in this particular case. Okay. So, so having said that, we know now that we can run at in this case, 3 1/8 gigabit. But what are the limits? Another question that you ask as a systems engineer: what are the limits of this particular link? What can we support? So one thing we can do is if we go in and we can sweep a whole number of things, many things. What I was going to sweep here is actually I have a sweep set up for data rate, where we can sweep 5, 6 1/4, 8, 10 gigabits per second. We know we can run 3 1/8 let's see what the performance of the link looks like as we increase this data rate. Okay, so a couple of things. While we're sweeping here, there's going to be 4 different sweeps that are running. Another capability that I'm not going to have time to show, but may also be of interest, is block sensitivity, where we actually can perform an automated sweep where we'll go through and replace each block in turn with a short circuit and rerun the topology, which allows us to dial in on the sensitivity of the overall link to the different blocks in the system. Okay, so the sweeping has come back, and again, we ran 4 sweeps, each one 200,000 bits apiece. If we look at the I heights here, we start out at about 250 millivolts. We drop to about half of that as we go up to 6 1/4, drop down to around 80 at 8 gigabits per second, and it's nearly closed at 10. So maybe with some auxiliary help, maybe at the 8 gigabit data rate, potentially there's something else we can do there. So let's go take a look at that. So I'm going to set this to run at 8 gigabits per second just to establish a new baseline. And we'll run that. So you can see how ease of use and rapid simulations allow you to do lots and lots of trade-offs that are very difficult to do otherwise. Okay, so initially, we have a lot of jitter. Of course, we've increased this up to 8 gigabits per second. Let's now turn on the decision feedback equalization at the receiver. And we'll see what the difference is here. So this is one of Sigridy's models. We have an example DFE model. Okay, and you can see the result here at 8 gigabits, right, with no DFE, but with the transmitter preemphasis, and then the results with the DFE in place. Okay, so it looks like actually this particular link may possibly be able to run at 8 gigabits per second if you use a SerDes combination that has both 3-tap transmitter preemphasis and also decision feedback equalization at the receiver. Okay. Okay, so let's go back and take a closer look at the algorithmic modeling, because obviously that was a big part of what we showed just in this demonstration. And in this case, this is one of the key aspects of being able to look at feasibility of some of these links. So if we're looking at algorithmic models, and this is still an area that is emerging in the industry as far as familiarity of the users. One of the fundamental concepts in the algorithmic modeling approach is to be able to separate out the circuit models and the algorithmic models. So if we look at this overall serial link, we've actually broken it into 3 pieces. One is the analog circuit channel, which we talked about, and that's circled in red. And again, that's the circuit that gets simulated to generate the impulse response. And then you've got the algorithmic models. In this case, there's one at the transmitter and one at the receiver. And those actually get all solved independently in the time domain. There's actually 2, IBIS AMI, a lot of people get confused with it. It can get complicated, but in its simplest form, it basically boils down to two interfaces that IBIS AMI standard allows. One of them is this first one, AMI init, and it's simply this is what was used for that transmitter preemphasis, and it simply takes in the impulse response of the raw channel, the analog circuit channel, the algorithm in the DLL, in the transmitter DLL in this case, decides how to filter it, and it passes back a modified impulse response. So when we looked at the modified impulse responses from the 2-tap and the 3-tap drivers, this is what we're looking at. In this case, the modified impulse response is then passed back to the tool and that's passed into the channel simulator for use in the convolution engine. Okay, and this is the simplest modeling approach, and it's typically used for one-time adaptive equalization. So, for example, it's a good application for pre-emphasis or de-emphasis, where it will set its tap coefficients one time and then transmit data. Okay. The second API or interface that's in here is called GetWave. It basically does the same thing as this first one, except instead of an impulse response, it takes in the raw waveforms of the channel from the channel simulator. Those raw waveforms, this is how a real device works, right? It emulates real hardware. It takes in real waveforms. The algorithm in the DLL decides, again, how to best filter it, and it passes the modified waveform back to the tool, along with, optionally, its sampling information or its clock ticks. And this is then the modified waveform is then post-processed by the tool to produce the eye diagrams and the bathtub curves and so forth. This is typically used for real-time adaptive equalizers. So, for example, DFE or continuous time linear equalizers, where the device real-time is looking at the waveforms that are coming in and making decisions and adaptations throughout the simulation run as far as how to best filter that. This is the correct interface to use in IVUS AMI for that. So, and of course, both are supported. And Sigrity takes a stance to be fully IVUS compliant with this. We expect to be able to easily run IVUS AMI models from any source as long as they're IVUS compliant. And this is again, this is an area in the industry where we're seeing improvements, where we saw initially some models non-compliant in the industry, but the ones that seem to be coming out now, by and large, are IVUS compliant and should be able to run in any EDA tool that supports IVUS. These are some of the example algorithmic models that are included with Channel Designer. There's a CDR, clock and data recovery model, continuous time linear equalizer, feed-forward equalizer, decision feedback equalizer. These two you saw in the demo, and advanced DFE model also. The ones that are included with the tool are very programmable. The intent there is to allow you to be able to very quickly do feasibility studies like you saw. Also, if you find a case where you need a model for a particular SerDes that's not available yet, the intent is that you can program one of Sigrity's models, hopefully, to mimic that device fairly closely so you can do some of your initial simulations. Okay, again, fully IVUS 5.0 compliant. We also have capability above and beyond AMI. For example, in IBM's case, they have an internal tool called HSS CDR, which we've provided direct integration to. It uses IBM. So if you use IBM IP, this may be of interest. It uses IBM's AMI models directly, but on top of that, also reads HSS CDR command files and library directly. And what this will do is automatically pull in the many dependent variables for the model and for the simulation that are based on the small set of user-definable independent variables that you can select for these different IBM cores. So, for example, you may select a particular data rate and core technology and corner, and those couple of independent variables may actually dictate a couple of dozen dependent variables, which we will pick up and automatically instantiate in the tool for you. Okay, next topic, power noise effects. This is an area that's often overlooked in serial links, especially for the lower data rates, but it's starting to become of more and more interest as people are beginning to push to the 8 and 10 gigabit data rate levels. This is a simple example that we had gone through to prove out some of this capability. This is a test layout, very simple one, a couple of components, a number of serial links routed between, got decoupling caps around each of the components. VRM, voltage regulator model placed in the bottom right-hand corner of this board, and also a footprint in the middle of the design where we can hook up a noise source for power noise injection. So what the power plane looks like. So basically, the power plane is one of the typical jigsaw puzzle power planes that you'll see in modern layouts. In this case, the ground plane actually goes all the way to the edges of this part. The topology that results from this, you can see the standard through channel that you see here, similar to what we've looked at before, with two additional items. One is the VRM circuit, where you're able to put a particular VRM spice subcircuit at that point on the PCB where the power comes in. And this will be the only place in the topology where an ideal voltage source is applied. That means that the transmitter and receiver will have to draw power through the PCB power planes, through the package PDS, and eventually through the on-chip and to the transmitter and receiver. The other one is a power noise source, where we've hooked up to that footprint that we put in the middle of the power plane. And this basically gives us a place to inject noise currents into the system so that we can see their effect on the overall eye diagram. Okay, and you can basically look at the PDS noise immunity of your serial link operating in the presence of some power noise instead of an ideal plane assumption. So basically what we did is we used the sweep manager. We swept the magnitude of the injected power noise currents. I believe in this case something on the order of 10 to 250 milliamps maybe, and just plotted out all the eye contours from the sweep manager, which you can do all in one shot. And as you can see, the eye does start to close down. The jitter increases. The eye height decreases as we increase the power noise currents. And the bathtub curves obviously are also affected. They start to narrow out as you get more power noise injected into the system and impacts your bit error rate performance. So this obviously this can be a key concern as you get into the higher data rates that you can account for these types of power effects. Okay. Now the extraction that we did for this, obviously Sigrity has a lot of technology in the form of PowerSI, which is an industry standard tool for power integrity analysis to extract the detailed power distribution systems. Can also extract them coupled together with the high-speed signals to extract this all in one model from your layouts. This is what was used in this case. Again, Channel Designer being extraction engine independent, there's obviously advantages to using PowerSI and some of the automatic linkage that you have with the larger subcircuits, say between package and board. But this extraction can be done with your favorite extraction tool as well, as long as it produces industry standard output like Touchstone. But this was an example that was brought to us from Skipper Lang at Delta Networks, where he characterized a particular path via structure for his differential pair with PowerSI and compared this with a full wave 3D solution. And you can see the time savings here and actually the close correlation at the higher frequencies. Okay, so again, it shows if you have PowerSI in-house, you can heavily leverage that to help you to build out your topologies for serial link analysis. Okay, so in summary, some of the different things that we covered today. So obviously, multi-gigabit serial link SI analysis presents some unique challenges. Okay, so it becomes very difficult to cling to ways that you've done in the past using traditional circuit simulation, simply from a simulation capacity standpoint, as well as dealing with some of the adaptive equalization in the modern SerDes devices that you come across today. And this brings a look at new tools and simulation techniques, some of which we presented today. Algorithmic models, IVAS AMI models, provide an efficient way to model adaptive equalization in these types of devices. Again, as long as you're able to receive IVAS compliant models from your SerDes supplier, you should be able to drop them right in and run not only in Sigrity's tool but in whatever your EDA tool is. Also, what we're finding is assuming ideal power distribution can give misleading and optimistic results in some cases. Again, especially as you push towards the higher data rates, we think this is going to become an area of increasing importance, and where we were going to try to provide additional automation and continue to work in this area to facilitate being able to model this with your serial link topologies. Ease of use, obviously, is a major factor. Our goal with this, just because of the sporadic use involved typically with SI tools, is that you should be able to sit down and build up topologies, run simulations for the first time in an afternoon. No new syntax to learn, all HSpice compatible syntax. Everything should be familiar, and basically if you can associate subcircuits with blocks and hook them together, you should be able to set up topologies and run. Okay.
Okay, so we had a bunch of questions come in, so let's take them from the top. So the first one for you, Ken, do all SerDes-based designs require IBIS AMI models?
Okay, so that's a good question, and actually it's a pretty common misconception. Everybody thinks when you're doing serial link analysis, you have to have IBIS AMI models, and if you don't, you can't do the analysis. So it's actually not true. IBIS AMI models are required for the SerDes devices, like I said, that use adaptive equalization, right, that adapt on the fly to the channel. Very difficult to do those with circuit models, so I would say mandatory usage for those types of SerDes applications. But there are actually lots of SerDes that are not using adaptive equalization, especially for the lower data rates. You can still use circuit models. People have been successful providing standard IBIS models for those types of devices, pre-emphasis, multi-driver sorts of devices, and even encrypted HSpice models in some cases. Those can also be used for that type of analysis. So while it's not mandatory, except for adaptive equalization really, even with, I'll say, static equalization, AMI still is a very convenient way to do it, and we've seen a number of devices modeled that didn't use adaptive equalization but still use the IBIS AMI approach for convenience. As you remember from the demo, we were able to sweep different types of analyses very quickly, changing the number of taps and various things by virtue of the fact that those programmable settings were included in the algorithmic model. So still big advantages for algorithmic modeling, even when the equalization is not fully adaptive.
Okay, I'm going to jump around a little bit because one of the questions that just came in kind of ties into this topic. How can you tell, this person asked, if an AMI model is good, and does Channel Designer perform model checks of any kind?
Model checking is usually done before you get to the tool. You should have some QA on your incoming models, just like you do with standard IBIS devices, standard IBIS models. One of the things that you can do right away is to run IBIS check on the AMI file that comes in, IBIS check-AMI file name .ami. That's something you can perform on all your incoming models. Also, as the models come in, there should be correlation data provided to you from the supplier of that model that will show that algorithmic model functioning as compared to whatever the golden source is, whether it's some other internal tool or transistor level HSpice or measurement or something else.
Okay. And I think you touched on this point, but a question came in. Is your solution fully IBIS compatible or tool specific?
Absolutely not tool specific. It's fully IBIS compliant. This is one area that Sigridy's taken a very strong stance on. We've seen a number of other models, especially early models, that have claimed to be IBIS AMI models that actually were not IBIS AMI compliant at all. Actually had vendor specific content. which we had to work with the systems customer and the IP supplier to help to correct. But I believe as people become more aware, more educated, and the standard becomes more mature, I'm expecting that the vast majority of models that SerDes suppliers will put out, really from here forward, should be fully IBIS compliant.
Okay.
But you do have to check. I mean, one thing you can do in the tool that helps quite a bit is you saw how you can go and look at the modified impulse response for those models that use the AMI init technique, and also you can look at you can even look at the raw waveforms pretty easily to see the before and after for those models that use GetWave. So there are a number of debugging techniques that you can use with the tool to help test out the functionality of those models, and we've used those extensively with the SerDes IP suppliers that we've worked with.
Okay. Okay, going a little bit of a different direction with the next couple of questions. So this person is asking about what's being used to characterize the channel. HSpice, he asks, and what if HSpice isn't available?
Okay, so so for our approach, as we had talked about, we use traditional time domain circuit simulation to perform that characterization process and generate that initial impulse response, which is very, very important, obviously, from the channel simulation standpoint that takes place after. You can certainly use, I mean, the default choice for us is to use SpeedSim, which is the circuit simulator from Speed 2000. Also because HSpice is so prevalent out there, and some circuits that we may have in our topologies may be encrypted HSpice. We see that commonly too. You can also point to HSpice as the circuit simulation engine, and if you do that, it will be used for the characterization process.
Okay, and since just as a follow-on, Ken, since you just mentioned SpeedSim, if someone was to access Channel Designer from Sigrity, would that capability come along with it, or is that a separate thing that they have to get?
No, the circuit simulator SpeedSim comes as part of the Channel Designer product.
Okay, and then this same person asked a somewhat related question. Let's see. What if you have, let's say, 100 channels, and what if there are 100 different unique impulse responses generated, and what are the implications of that?
Right. So really, from here, we have the capability to analyze serial links in detail. The next step is really to go to a little bit higher level and provide some kind of screening capability so that you can screen through these very large designs that we see and be able to pick out the couple of serial links that you want to analyze in greater detail. So those screening capabilities are techniques that we're actually working on in Sigrity today.
Okay, so there's a little bit going forward development on that, but for now you'd certainly also take advantage of doing some work to figure out which part of your channel is most apt to have a problem, zero in on those things first. And
that's right. I mean, people are using their existing layout level tools, including Sigrity, Speed 2000, and PowerSI to help to identify those nets. And there's also, in some of the larger companies, there's internal techniques that they've developed also to perform some of the screening capabilities.
Okay. Another person asked another question about the models. They wonder about IP protection and how easy are the compiled models to disassemble.
Well, I mean, the purpose of providing those algorithmic models in DLL format is so that they can't be disassembled. So that code is like it's like executable code you see in the software that you buy and license, and you should not be able to break into that IP and see it. Basically, the external window into that DLL will be the AMI file, the text-based AMI file, which limits you to look at the parameters that the modeler wants you to be able to configure yourself. So, we've seen even the largest IP suppliers have all adopted this approach and have gone forward comfortable with the IP protection that the DLL format provides.
Okay, and this same person asked kind of a follow-on question. Can I hide my device jitter parameters inside the compiled AMI file?
You have the, well, yeah, you do. You have the ability to, as a modeler, you can take a couple of approaches to jitter. One is an external approach where you allow the tool to inject whatever jitter you want to have associated with your devices into the tool. You can also do that completely transparently inside the DLL. So we've seen cases with that as well, where actually the internal jitter will be handled by the DLL, especially in the cases of some of the advanced receivers that we've worked with.
Okay. And a question coming in from sort of a different direction. Can Channel Designer handle nonlinear drivers and receivers?
There can be some nonlinearities in there. The thing with the multi-gigabit serial link drivers is that by nature they have to be very symmetric and very linear, or they just wouldn't work at multi-gigabit speeds. So, I mean, it's a very different animal than some of the parallel bus I/O models with the totem pole push-pull outputs where you have some major nonlinearities. These tend to be, again, by nature, very linear and very symmetric, and we've had very good success, as you've seen in some of the correlation slides, in being able to correlate these back with golden waveforms. But you know, if a driver was highly nonlinear in its circuit model, then these techniques probably would not be a good fit for that. But for multi-gigabit serial links, that is typically not the case. And you can have nonlinear effects in the equalization in the algorithmic part of the models. That's actually fairly common. It's really in the circuit part, the output stage of the transmitter, the input stage of the receiver, where that lies.
Okay. Another person is asking about the simulation time that you showed in the demonstration. He wants to know, does the solve time increase in a linear way with the number of ports or frequency points, or and are there some interpolation techniques that still allow you quick yet accurate solve?
Well, you saw real time, the entire simulation. I purposely did that, including the characterization step. So remember, the first time, actually, the SPICE circuit simulator ran to generate that impulse response. In that case, that was a fairly detailed through channel topology with large S parameters that ran in about 15 seconds, I think. And then the 200,000 bit simulations ran in the order of somewhere between 5 and 10 seconds. And we see it basically linearly increase as you increase the number of bits. So whatever your first simulation is, let's say for 100,000 bits, if you're going to run 1,000,000 bits, it's going to take about 10 times longer.
Okay.
That's what we see.
Okay, so we have, it looks like two more questions that will kind of group, I group them together a little bit. So the first of these, since they have to do with a similar topic, at what point are engineers moving away from ideal power assumptions for serial link design?
Well, I mean, everybody started off with the ideal power assumption, basically because that was sort of a limitation in a lot of those tools, and they've served them pretty well for the lower data rates. I guess anecdotally, what we've seen is as people have gone to really 8 to 10 gigabit channels, they start to become very concerned with the non-ideal power effects.
Okay. And then another person was asking a question that I believe tied into that, because it was a question that came up in connection with one of the slides. And the question is, for the handling of some of these non-ideal power effects, is this capability coming from the extractions being done in PowerSI, or are there also some capabilities inside Channel Designer that address the topic?
Well, Channel Designer, generally speaking, is independent of the extraction engine, but we've obviously built some additional capabilities taking advantage of PowerSI's ability to efficiently extract those kinds of networks, where you'll see in the upcoming release of Channel Designer, you'll see some direct integration where you'll be able to associate lay out files with different blocks in the topology, and basically be able to leverage PowerSI in the background to go and populate those blocks on the fly, extract the S parameter files, and build subcircuits and link them together in an automated fashion. So you can use whatever extraction engine you want, as long as it's using industry standard output formats that we can use, basically HVICE compatible output formats and Touchstone and BNP and so forth. But of course, we're trying to build additional integration with Sigridy's own extraction engines to try to make that task simpler.
Okay, good. I think what we'll do then is leave it there, and really appreciation goes to everyone who participated, and certainly to you too, Ken. I did notice that some people joined us late, so we will certainly be sending a link for a recorded webcast to all of those who participated. So again, thanks to those of you who did participate. Send us a note if you have additional questions. We certainly can arrange for individual discussions with design teams who are encountering these kinds of issues. So that's it for us. Thanks a lot.
Thanks, everybody.